Welcome to the third part of the problem-solving session for Chapter 10. We begin where we left off, question 9. 4 particles are on the xy plane as shown. Assume that the particles labeled with capital M have a larger mass than the particles that are labeled with the small m. But consider the distances of the masses A and B to be equal. So in other words, the distance A equals the distance B. Now these 4 particles or point masses are fastened to the corners of a frame, and of course that would be the frame here and the frame here, but the frame has negligible mass. So all that the frame is doing for us is anchoring the masses at the fixed positions A or B. Now we're told that these masses can rotate either about the x, the y, or the z axis. And in part A, we're asked to determine about which coordinate axis is the moment of inertia the largest, and about which coordinate axis is the moment of inertia the smallest. Now in the diagram that they've drawn for us here, we have a rotation about the y-axis and a rotation about the z-axis. So in other words, here, if I could have the 3 dimensions, the third dimension, the z-axis, would be coming out at you in the positive and away from you in the negative. So the rotation is, for example, this way if it's counterclockwise. Okay, so we're looking down onto the masses. Well, the only one that's missing here is a rotation about the x-axis. So what might that look like? Let's see if I can go ahead and do a drawing for you. Here's a capital M, another capital M, a small m, another small m, and the rotation here would be about the x-axis. So here's x and here's y. Okay, well let's proceed to determine the moment of inertia for each one of these situations. Here, the moment of inertia that we are going to use, the expression we're going to use, will be for discrete masses. In other words, we don't have to do any integration because these are point masses. And so all we have to do is to consider each mass multiplied by its position, its distance, to the axis of rotation squared. So in this first situation, we have the following. We have, if this is the axis of rotation here, notice that both of the small m's are located right on the axis. So technically, their value for r is 0. They are on the axis of rotation. On the other hand, the 2 capital masses are at a position r equals a to the axis of rotation, each of these. So we get no contribution from the little m's, but we get the contributions from the large m. So we have capital M times a squared plus capital M times a squared gives us 2 capital M a squared. What about this situation here? So this is a rotation. This one was about y. How about x? Okay, here we can make a similar argument and say that the capital M's are located right on the axis of rotation, so their r value will be equal to 0. On the other hand, the small m's have a value r equals b, which, don't forget, a equals b, so we can just write both of the b's in terms of a's, so we can compare a's with a's. And so here, when we calculate the moment of inertia, m times r squared, we get small m times a squared plus small m times a squared gives us 2 small m times a squared. But don't forget that capital M is greater than m. So far we see that the rotation about the y is greater than the rotation about the x. What about the rotation about the z-axis? And I have to move a little further here about the z-axis. Now this time, however, because the z-axis, let's come have a look. Because the z-axis is perpendicular to this plane right here, both capital M's are a distance a away from the z-axis. See, the z-axis is in the third dimension coming out at you. And both of the small m's are at a distance b equal to a from the z-axis. Therefore, we're going to get contributions in both the small masses and the large masses. So here, m r squared, we get small n times a squared plus small m times a squared plus capital M a squared plus capital M a squared. And so we end up with 2 small m a squared plus 2 capital M a squared, making rotation about the z to have the largest value of moment of inertia, rotation about the x-axis having the smallest moment of inertia, because remember that lowercase m was a smaller quantity in mass. Okay, next problem. Rigid rods of negligible mass. In other words, we are to assume that this rod is massless, and all it does is it anchors our point masses at their fixed location. Lies along the y-axis connecting 3 point masses as shown below. Where is the center of mass of this system of 3 masses? And if you could shift the axis of rotation to coincide with the location of the center of mass, what would be the moment of inertia about an axis that runs through the center of mass and parallel to the x-axis? Well, let's tackle the first question, which is to determine the location of the center of mass. Well, we know that because all the masses are on the y-axis, the center of mass in the x is 0, and here we are dealing with point particles, so all we need to do is to sum the m's times their respective y's, okay, divided by the total sum of the mass, which is the total m's, okay? So let's see. Let's start with, let's call the 4 kilogram mass M1, and we have its location at Y1. The 2 kilogram mass M2, its location on the y-axis, and M3 is the 3 kilogram mass with its location. So we have 4 kilograms times 3 meters plus 2 kilograms times minus 2 meters plus 3 kilograms times minus 4 meters. Divide that by the sum of the masses. 4 plus 2 is 6 plus 3 is 9 kilograms. And all the kilogram units are going to vanish. They're going to cancel, common in both numerator and denominator, as they should. And our value for y center of mass is minus 0.444 meters. So in other words, the center of mass is just below the origin along the y-axis. Okay, now what they want us to do is to shift the axis of rotation to coincide with the center of mass. So the rotation now is not about the x, but it's about the this particular axis that runs through the center of mass, okay, which we've just worked out that it's at minus 0.444. So to determine the moment of inertia, the definition for point masses is m times r squared, where r here is different than y or x because r is a measure of the distance from the mass from m to axis of rotation. So now we have to take into account where each of these masses is relative to the axis of rotation. So let's see what happens with the case of M1. In the case of M1, the 4 kilogram mass, now R1 is equal to 3 plus, see this little distance here, 3 plus 0.444. See, now we're not subtracting it, we're adding it because R is this distance right here. And R2 now is 2 meters minus that distance because here's R2. So R2 is going to be 2 minus 0.44, which is 1.566 meters. R3 is this distance right here, which now is going to be 4 minus 0.444, and that gives us 3.556. So you see R is really a different quantity. It's not the location, but it's a distance, and we have to keep that in mind as we do our work. Okay, and remember that moment of inertia does not get divided out by anything. So we have 4 kilograms times the 3.444 meters squared plus 2 kilograms times 1.556 squared plus 3 kilograms times 3.556 squared. And that total works out to be 90.2 kilograms times meter squared. Okay? Next problem. Okay, here the images didn't come out, but on your notes you will notice that the rod in this case is located here, and in this case the rod is located here. So let's go ahead and read the problem. It says a rod of length L has a uniform mass density. This right here, uniform mass density. Remember that lambda, the uniform mass density, is when it's constant, as is the case here because of the word uniform, is a ratio of total mass to total length, which should be the same numerically as small mass to small length. Okay? So anyway, these are not discrete masses now. These are masses that are so infinitesimally small that when we sum them up, we have to integrate. Okay? But because of the uniformity of this mass distribution, we immediately have a relationship with the mass density and the total mass to the total length, and dm over dx, where we're going to take the x-axis to be the axis about which this very thin rod lies. So let's draw our x-axis there. So anyhow, it's rotating about an axis through its center of mass perpendicular to its plane. Okay, now that is the first case here. So you can see that the center of mass here, this would be minus L over 2. This is L over 2 because the center of mass would be in the true center. The entire length is L. We want the moment of inertia as it rotates about that center of mass axis and also in part B about its end. So in this case here, the left end is at the origin and the right end is at L. So in other words, we have to do an integration. And so what we need to do is, in each situation, we have to select a representative of dm, a little dm, which of course will have the infinitesimal length dx. This is our little dm, and will be located at a distance x from the axis of rotation. The same is true here. It doesn't matter which one we pick. Here's our dm, here's our dx, and here is the position of dm relative to the origin. And remember that in this case, we're summing all the dm's beginning at minus L over 2, the left end of the rod, all the way to positive L over 2, the right end of the rod. Here, we're summing all the dm's from 0, which is the left end, to L, which is the right end. Now, once again, if this is our first step, our second step is to write dm in terms of lambda dx, okay? Knowing that lambda, which is a constant, is also equal to m over L. Now, when we were doing the center of mass calculations, we always just left lambda as lambda because we had lambda both in the numerator and the denominator, and so in fact lambda canceled. We never had to worry about the actual value of the relationship of lambda to mass and either length or area or volume. Here, when we do a calculation of the moment of inertia using the definition, which is the distance of the element of mass dm to the axis of rotation, and that distance being squared, there is no denominator. And so what we'll want to do is to substitute the lambda for m over L, which is a constant anyway. Anyhow, let's see. In part A, here's what we have. We're summing all the dm's from minus L over 2 to positive L over 2. R is the position of the dm relative to the axis of rotation, so r is equal to x in both cases. So we have minus L over 2 to positive L over 2 x squared dm, where dm is lambda dx. Okay, that's our dm. Further, because we're not going to be canceling the lambda with anything in the denominator, knowing it's a constant, we pull it out of the integral, okay, over here, and so we're left with minus L over 2, positive L over 2, x squared dx. One more step is to substitute the fact that lambda is equal to m over L, perform the integration, which will give us x squared dx. Integral is x cubed over 3 from minus L over 2 to positive L over 2. So let's see. We have m over L and L cubed over 8 times 3, the 3 that was already there, minus, which gives us a plus, L cubed over 8 times 3. Well, L cubed over 8 times 3 is, this is 24. We're going to cancel this L and make this L squared and this L squared. So we're left with m times L squared over 24 plus L squared over 24 is 2 L squared over 24. And that gives us a value of mL squared over 12. Now that is for rotation about center of mass, okay? This is moment of inertia. What if we're rotating about the left end? In this case, everything is the same, except if we come over here where we set up the integral, here our endpoints are going to be from 0 to L because we are summing the first dm at x equals 0 and the last dm at x equals L. So we're still going to have lambda integral x squared dx, but the difference is going to be 0 to L. So let's go ahead and write this out. Lambda integral of x squared dx from 0 to L. Lambda again is m over L. This integral is going to be x cubed over 3. And this time just from 0 to L. And you can see that this will give us m over L times L cubed over 3. This L will cancel 2 of those. And so I here is equal to m L squared over 3. Now there's something else I want to say about this, and that is that we can easily use the parallel axis theorem to eliminate one of these integrations that we did, because the parallel axis theorem says that the moment of inertia about any axis that is parallel to the axis through the center of mass is given by the moment of inertia at the center of mass plus the mass of the rod times the distance. This is the distance from the center of mass axis to the parallel axis. So let's see how we could have eliminated having to do this integral right here. If we know that the moment of inertia through the center of mass, as we just worked out, is ml squared over 12, we take that and we add m times, well, let's see, the center of mass is at L over 2 from the end, so we take L over 2, square that, and this gives us ml squared over 12 plus ml squared over 4. When we add these up, we get none other than ml squared over 3. So in other words, we didn't have to do this integration here had we used the parallel axis theorem. Okay, next question. Here, I'm going to work out two integrals for you. I'm not going to do the three-dimensional integral. I'm simply going to do a one-dimensional integral, which is the first part of this question. And this is that there is a hoop, a very thin hoop. So in other words, it's so thin that you can consider it to be a line. And it's going to be rotating about the center. It has a radius r. Okay, so the rotation is about an axis that passes through the center, which is already, by the way, the center of mass. And we have to determine the moment of inertia in this case. Let me see if I can just get rid of this right here for now, because it's more of a hindrance than a help. Let's delete this, and let's delete that because I won't be doing that. That is a three-dimensional integral, but I will do the two-dimensional integral, and that's all I'll hold you accountable for. So the first thing we want to do is to set it up where we have an actual element of mass, a little dm. Right here's our little dm. Now this, of course, is our d theta, this, the little arc length of this little mass element is ds, which we also know, if this is the radius, which by the way is constant in here because all the little mass elements are a distance capital R from the center of rotation. So ds is r d theta, and this is our little dm. Well, as always, in this case, one dimension, lambda is total mass over total length. What's the length of a circle? The perimeter, which is 2 pi r. But that should also equal dm over ds. In other words, a little element of mass dm over the little length of the arc that it describes. So in other words, here, solving for dm, we see that dm is equal to lambda ds, or using the definition of ds, lambda r d theta. So before we actually do this next part, which I'm going to cross off, let's go ahead and work out this first part. So we've set up our integral. Now we have I equals the infinite sum r squared dm, and we're going to sum all the mass elements from 0 to 2 pi. In other words, starting with 0, if we want this to be our x, all the way around. And all of the little mass elements dm are going to be fixed at a distance capital R, the radius, from the axis of rotation. And we just obtained the value for dm as lambda r d theta. So our integral becomes, lambda comes out, it's constant, r squared d theta from 0 to 2 pi. But guess what? R squared is also a constant since R does not vary with angle. All the mass elements are fixed at a position R squared, and so really this integral is just the integral of d theta from 0 to 2 pi. Well, let's see. M, we said, lambda, we said earlier, is capital M, the total mass, over 2 pi r. Multiply that by r squared. The integral of d theta is nothing more than theta. And theta runs from 0 to 2 pi, which gives us the value of 2 pi from the integral. This 2 pi cancels that 2 pi. This r cancels one of these r's. And so the moment of inertia here of this hoop, or thin ring, whatever we want to call it, is mr squared. Okay, what if instead of a thin ring, we have a solid disk? Let's draw the solid disk. This time, the disk is not hollow, it's not a circle, it's now an area. So what we want to do is that we want a representative dm, which this time is going to be an area. Its length will be described by d theta, so this is our d theta. This little element of length here is ds. This little element of length here is dr, and the location of dm, our little dm, happens to be a distance little r from the axis of rotation. So the rotation's about here. Now again, ds is going to be equal to r d theta, but we're not using capital R because we have to sum all the little mass elements from r equals 0 to r equals capital R, and over from, we're going to sweep from theta equals 0 to theta equals 2 pi. So we're going to have a two-dimensional integral. Okay, let's see. dm is equal to not lambda anymore, but sigma, because now we have an area. dA. What is the area dA? Well, let's see. We have a dr times a ds, right? That describes the area. So dr times ds, but ds is r d theta, so dr times r d theta. This is our dA, okay? And so dm can be written as sigma times r dr d theta. So this is our part 2. Now we're ready to proceed to the actual integration. Here, r squared dm is going to give us double integrals because we are going to have to consider all the mass elements from 0 to r and from 0 to 2 pi. So we have two integrals. And r is no longer capital R because we're summing all the r's from 0 to big R. So our integral becomes 0 to 2 pi, 0 to r squared times dm, where dm is equal to sigma r dr d theta. Now, we can clean this up a little bit and take sigma out of the integral. The first integral is going to be, d theta is going to be constant when we perform this inner integration, so we might as well put it out here. We could do this, here we can do this first. Let's see, 0 to 2 pi. And if we do this integration here, the d theta is constant, so it comes out of this integral. 0 to r squared, r cubed, right? Because we have an r squared times r, dr. So again, the d theta was constant. It does not vary with the value of r. We're still summing from 0 to 2 pi, so we pull it out of this integral, which then fits it into this outer integral. So we have lambda is equal to total mass over total area, pi r squared, because now this is sigma, which is mass per area. From the outer integral, we're going to get theta from 0 to 2 pi, giving us 2 pi. From the inner integral, we're going to get r to the 4th over 4. When we substitute the endpoints, we get capital R to the 4th over 4. And we clean this up a little bit. This pi cancels that pi. This r squared cancels 2 of those. This cancels 2 of these. And so we're left with mr squared over 2 as the moment of inertia of a solid disk. Now, notice that this moment of inertia has half the value of the moment of inertia of the hoop. And that is because we have some mass elements distributed closer to the axis of rotation, whereas in the hoop, all mass elements are distributed at a distance, capital R. Now, in the notes, you saw that for the solid cylinder, the value was the same. I was equal to mr squared over 2. I did it as a three-dimensional integral, but what I want to show you is that it doesn't matter what the length of the cylinder is, whether it's as short as a disk, meaning no third dimension, or as long as a long cylinder. All mass elements are considered as if they are as far away from the axis of rotation as the disk, because the length runs along the axis of rotation and is insignificant. Well, this concludes the third part of the problem-solving session for Chapter 10. Until next time.